Hello all and welcome back to this course on computer organization. So having looked at various calling conventions, the STD call, the CDECL call to handle variable argument lists and the fast call, right? It's also good for us to just understand what happens in C++ programs, okay? So this lecture will be a very short comparison between C and C++ at assembly level, okay? So C versus C++. Now, C++ is an object-oriented program, so therefore it is very different from C because it's more a way of thinking rather than a programming language. Okay, so it allows you to cast real-world problems the way they should be because that's how they are, in the design, and therefore they are very easy to implement if you cast them as classes and objects and you inherit and stuff like that. Okay, so I am not going to talk about object oriented programming or OOPS out here. That's not the focus. What I want to really look at is at an assembly level, at a microprocessor level, what is the difference between C and C++? Because C++ seems to be a higher level language than C, right? And in fact, this can be extended to Python and Java and so many things, right? There are so many languages which are sort of derivatives of C, which are very powerful. But at the assembly level, at the microprocessor level, is there any fundamental difference? If there is such a difference, what exactly is it? That's the focus of this discussion. Okay, for that reason, I have started with this very simple program here, which basically has a class. Okay, this is, remember, now I have moved my programming language to C++ on top here, and I am still sticking to x86 MSVC latest and all that. Okay. So there is a class A which basically has private member variables A and B, okay, and there is a public function init to which I pass values x and y, and inside the function there are local variables u and v, and I am initiating the member variables A and B to x into u and y into v respectively. Okay. On the other hand, I have a structure. Okay, sta int a comma int b, and that's it, right? Then I have a function out here that takes a pointer to the structure int x comma int y, just like the previous init function, and I am saying u equal to 200, v equal to 400, all that is the same. Whatever pointer I have passed, pa arrow a, means you are taking the pointer and then initializing this member variable of the structure with this value x into u, y into v. So you see that this code and this code is very similar except for the way we have accessed those variables a and b. One is through a pointer, other one just seems to be without anything. Okay, it's just associated. Therefore, if you now ask me what is this a and b, well, I can't say because this depends on where the object is actually instantiated and what the memory location for that is. Now coming to the main, I have int x equal to 7, x equal to 6, y equal to 7, a class, an object A which is of the type of the class A, and object B which is of the type sta. Okay, and then I am saying object A dot init x comma y, and I am saying on the other thing for the structure, I am saying init of ampersand object B x comma y. Okay, so what we have done here is the way we have accessed the function init is through object A dot, whereas this function is just a direct like any other C function call with a pointer to the object. So remember, the pointer itself is always just 32-bit. It's a D word because it's an address. It doesn't matter whether that pointer is pointing to a structure or an integer or a double. In fact, that's why you have the concept of a void star pointer, because the void star pointer, that data type is still just 32-bit. It's just an address. Now you have to define what it points to in order to do pointer arithmetic, like a plus plus. If you say pa plus plus, then you have to define it to be an integer, then it will go up by 4 or 1 or whatever it is, right? So now What is the difference between these two function calls, object A dot init and init of ampersand object B? This is what we are going to look at. Okay, so you see here, first of all, the main is translated here. This is the prologue, right? And then I am doing the initialization of x equal to 6 and 7 and all that. And then this is my function call for the member public function init of that object A. Okay. So what have I done? I have basically said, I have called init of x comma y. So you look at this particular call. Okay. It does something very interesting. It is moving y into EAX and then pushing that into this thing, because you are doing x comma y. So it will push y first onto stack through EAX, then it is moving x into ECX, pushing ECX, and then it is doing something interesting here. It is doing LEA ECX comma d word pointer of thing. So what does this? So object A, by the way, is minus 16. Okay, so remember, in C++, so the object A dot init of x comma y, right, gets translated to move EAX comma contents of EBP. So what is this? Let me look at this statement here. EBP, x is EBP minus 8, right? So this is EBP minus 4 that I am doing here. Okay, and then push EAX, then move ECX comma EBP minus 8, this is x, push ECX, and then you are doing LEA of ECX comma d word pointer, right, of EBP. What is this? Minus 16. Okay, because this object A underscore A, as you can see here, is minus 16. So EBP minus 16. So this is basically saying ECX equals EBP minus 16. It seems to have the address of that object A, obj A, that is sitting in main. Okay, and then you are doing call of the function init. So first thing you notice is, even in C++, there is nothing that has changed in terms of how a function is accessed or a function is called. Pushing parameters, everything is exactly the same. By default, in C++, the C++ calling convention also is like a cdecal calling convention. You are going to do the stack cleanup after you return. That's why when you come back from here, right, you do class A and all that. Let me just check that. Yeah, so okay, here it seems to be by default, if you look at the class init function, stack cleanup is happening in that function itself. So by default, it is like a STD call. Okay, so that's the important thing here. Okay, so call init, and there is no stack cleanup after that. If you go to the implementation of this function here, it seems to be doing something very similar, but we'll come back to that a little later. Okay, now let us look at what is happening to this call. It's a structure with very similar member variables, and you're calling an init function, but you have to pass the pointer. So the only difference now is, if you look at this, you're doing exactly the same thing. Move y into EDX, pushing EDX, move x into EX, pushing EAX. Then you're doing LEA of this. The only difference, right? So let me put that here, right? Init of ampersand objb comma x comma y, right? This is translating to something very similar. So I may want to give myself a little more space here. Let me just move this out. Okay, and this also, let me move it here. Yeah. Now this seems to be doing exactly the following: push edx, comma ebp minus 4, right? Sorry, move first and then push edx. Okay, so y is getting pushed onto stack out here, right? And then you're doing edx, and what's the other this thing, ecx again. Move ecx, comma ebp minus 8, right? And then push ecx, right? And then you're doing lea ecx, comma same thing, okay, d word pointer by the way, of ebp minus, this time it's not 16 because we are talking of object b, which is minus 24. Okay, and now you are doing push ecx and then call init. So if you look at these two function calls, right, with very similar structure and classes, the only difference happens to be this particular instruction. You are pushing ecx onto stack, you are doing the lea, right? So if you look at the stack in the main, by the way, right, so the stack in the main is going to appear like this. Okay, so this is my struct object a, which is sitting here, right? So this is what ebp, so let's look at it, ebp minus 4, this is local variable y x, so this is ebp, right, ebp minus 8. Then this is my object a, why? Because this is ebp minus 16, object a, right? So this is object a with member variables a and b, so this is object a in main, right? So ebp minus 8, ebp minus 16, and then ebp minus 24 is here. So this is some ab and this is object b. Okay, so maybe I'll remove this line to indicate that it's a structure or a class. Okay, so all we are doing now is we are getting the address of these two variables into ecx. In one case we are calling init without pushing that onto stack, in the other case we are pushing it onto stack and then calling init. Okay, therefore the guys on the other side, the function also has to expect the same. Okay, so if you look at this structure here, the prologue is exactly the usual stuff. You are moving ebp, then ebp comma this thing, whatever, right? And then how are you accessing the member variables a and b? You look at this, right? Basically all that is being done through pointers. Okay, move ecx comma this thing, then you are doing contents of ecx out here to get the value of eax. What is the eax? Eax is nothing but the x into u. Okay, getting that. Similarly, you are doing for the other value also, you would be doing something very similar for the contents of in PA arrow B. Also, you would be doing something very similar, right? So the pointer arithmetic and not the pointer, the pass by pointer seems to be the way in which you are actually setting these member variables. So because when you do PA arrow A equal to, you want the variable in the calling function, that is in main, to actually get that value. Okay. Now when you look at what is happening in the C++ function init, right? The only difference, so you look at the prologue, it is very similar. Okay, same subtract ESP comma this thing. The only thing is, now the address that we got in ECX is now being stored as a local variable in that function before you proceed. So what is actually happening is, every object of a C++ class, right, of a C++ instance has something called a this pointer. Okay, so actually inside this inside this particular function here, right, inside this object of init a comma b, right, so here for example init init of int x comma int y, when I say a equal to x into u, it means this arrow a equal to x into u. Implicitly this is what it means. Okay, so that is why I can actually pass the variable, the address of the this pointer, right, that is the object, that is the object of the address of itself is being passed through a register to this function. Okay, so in fact I can go here and in fact change this if you want. I can say this arrow A and this arrow B. It will still give you a very valid compilation and it will translate it to the exact same assembly output that we have. So now you see this, the structure of these functions are also very similar, except that the pointer address is coming implicitly through this pointer. Now because there is only one this pointer, I don't need to pass this through the stack, I can pass it through a register. And the convention in this case happens to be that you are choosing ECX to pass the value of the this pointer to the function init. However, in order to free ECX so that you can use it for computation in the function, you are putting that on the stack, right? And that's why in this function here, when you get into init here, right, that guy will have the value of this pointer as the first variable on stack out there. So you look at it, you will get move dword pointer underscore this comma ECX, right? And what is underscore this? It is EBP minus 4. So when you are in that function, right, so when you come to that particular function here, right, you will call, so let's say when you are calling this guy, what is going to happen? You will first push the value of y, you will push the value of x, then you are not doing any this pointer pushing, it is calculated in ECX and just sent over, then you are calling it, so this will be y, x, the return address, right, and then you are going to say that I am going to push EBP of main out here, right, and then you will bring EBP up to this point and out here you will put the this pointer. So EBP minus 4 will be the first local variable whose value will be the address of the object that is passed to it, and therefore every dereferencing of a member variable will happen through that pointer here. So that's why dword pointer of ECX, this, that and all will happen through this guy, right? So the two programs, the two functions we have written in principle are the same, and that is exactly how the C++ calling convention is handled in assembly language. Of course, C++ also has private, public, protected and all that. It has templates, it has so many other things, but all these are just compiler gimmicks. Okay, compiler will check whether you can access that private variable or not. Okay, so if I have a private function and I try to access it directly from main, it will not allow me, but that is just a compiler check. It's not that at assembly there is some check to say, oh, this is a private function, I cannot access it. No. Once you go past that compiler stage, every function looks exactly alike in C and C++, except for that calling convention where you are passing this pointer through ECX. Okay, likewise templates are just a lot of pre-compiler gimmicks. Eventually they get translated to some simple stuff like this that we have seen in C. So in summary, there is hardly any difference between C and C++ at an assembly language, which is hardly surprising because the microprocessor can do only certain things, and therefore whatever language you write, ultimately the compiler has to generate an output of assembly which can exploit what the microprocessor can do, and C or C++ or Java or whatever has to do something very similar at the lowest level. Thank you.